Swayam Prabha. Digital India. Educated India.
In this video, we will look at the different types of convolutions that are typically done in a convolutional neural network, and especially focus on the dilated and transposed convolutions, which are often used in deep networks and also in networks that have the encoder decoder type of architecture. So, just to recap, this is what we call naive convolutions. So, this is the typical convolutional operation that is done on a deep neural network. So, we have a given kernel size, we have a given kernel size k, stride used in the convolution and the padding, and given as input feature map of size I, IW and IS, high h, width and height. The output feature maps width and height are calculated by these formulas. So, it is the size of the feature map minus the size of the kernel plus 2 times the padding divided by the stride plus 1, that is the width. So, the typical same formula applies to the height also. So, this is the operation that we typically see. This involves superimposing the filter kernel, which is shown in red here, over the green input volumes, and then striding it across the input volume. So, just to illustrate, so if you go back, that is the first element calculated here by superimposing the 3 by 3 volume, and then once again we do the same by moving the filter kernel by one stride of, in this case the stride is actually 2, even though it is written as 1 here, it is actually 2 stride of 2, and we repeat this calculation throughout the cross section of the feature map. Now, dilated convolutions again are another convolution that are used to increase the receptive field of the convolution given the same given a smaller filter size. So, it is a cheap way of, cheap in the computational sense, way of getting a larger receptive field using a smaller feature kernel, filter kernel. So, for instance, in this image we have this input feature map in green and the filter kernel is of size 5 by 5, and as we saw earlier, we just move the filter kernel across the feature maps in order for us to obtain the output feature map shown here. Okay. Now, the idea is to use a 3 by 3 convolution with the dilation factor that can visualize the same area as a 5 by 5 convolution, while the number of parameters remain the same. That is, basically you have 9 parameters instead of the 25 parameters used in a 5 cross 5 convolutional kernel. However, by having a dilation in there, we can get the same receptive field size. So, how do we accomplish that? So, what is shown here in this image is that there is these red elements correspond to the elements of a 3 cross 3 feature map, and by incorporating appropriately rows and columns of zeros, we are making the size of the feature of the filter kernel 5 cross 5 and then proceed to do convolutions as before. Okay, so, this is very advantageous in the sense that you will with little computational expense, you are able to get the same receptive field size. If we recall, as we seen earlier, in order to get a receptive field size of 7 cross 7, it is the same as doing 3 cross 3 convolutions in succession. So, that is an increased number of operations, while in this case we directly get a 5 cross 5 receptive field just by adding appropriately adding zeros and 0 columns in the rows and columns of your filter kernel. The number of rows and number of 0 rows and 0 columns that you add is referred to as the dilation factor. Okay. So, just to recap, the idea is to inflate the size of your kernel by inserting rows and columns from zeros, so that you can get a slightly larger receptive field. The next topic is the transposed convolution. Here, the idea behind transposed convolution is to aid in increasing the size of the output feature map, and these are typically used in encoder decoder networks, especially on the decoder size, so as to increase the size of the feature map as you go towards the output. Okay. The idea is to regain the original spatial resolution, not to regain the actual feature map itself, but just to regain the original resolution, that is the size of the feature map. And you have to appropriately pad with zeros and also insert zeros and zeros in rows and columns of your input feature map in order to obtain the appropriate sized output. Okay. The good way of thinking about it is to see that how do the idea behind the transpose convolution is we interpret the input feature map. Let us say the input feature map is of size 2 cross 2, okay, and you have also been given a kernel size, okay. Let us say this is a 3 cross 3, okay. Now, we want to get a certain sized output, okay. It is given, let us say this is some m cross m, we do not care, okay. So, what we have to do is we have to understand this, just that you assume that the input that you are given to the transpose convolution, this is the input to the transpose convolution, is an output of as a direct convolution, okay. So, we have to find out what feature map size when operated upon with the kernel size of 3 cross 3, okay, given the padding and stride are given, will give this output size, okay. And diluted convolutions, we try to regain that particular, we try to get that particular input resolution, which is basically trying to reverse that operation. Here once again to reiterate, we do not seek to get the input and in fact reconstruct the input feature map, but just to regain the resolution. The example given here, so you want to reconstruct this size, right, or you want to reconstruct this resolution, 5 cross 5 is your target output, and your input is actually a 2 cross 2 feature map given by these green squares. So, it is actually a 2 cross 2 input. Your filter kernel is of size 3 cross 3 given by this gray, okay, and you seek to obtain a 5 cross 5 output, okay. Now, the stride parameters are given. So, if you think about it, the idea is what filters, what input feature size when convolved with a feature map with a filter kernel of size 3 by 3 would give rise to a 2 cross 2 output, right. So, that is what we would have to figure out. So, it turns out that this is 5 cross 5, and the idea is in order to regain this 5 cross 5 size, we have to actually have these zero padding on the outside. So, 0 padding of 2, and we also need to have this 0 columns and 0 rows inserted into the input feature map of size 2 cross 2, and then proceed with the convolutions as before, okay. So, for instance, let us just understand this better. Let us say your input size is 5 cross 5, okay, and your kernel size is 3 cross 3. If you do a naive convolution, then you would get the output size would be 5 minus 3 plus 1, which is 3 cross 3, okay. So, which is not what we want. So, if you want to get a 2 cross 2 output, what do we have to do? So, let us say we have a stride of, we add a stride of 2, in which case your output size would be 2 cross 2, okay. So, if we have a stride of 2, no 0 padding, and we have an input feature map of size 5 cross 5, and your filter kernel is of size 3 cross 3, then with the stride of 2 your output feature map would be of size 2 cross 2, okay. So, now we want to reverse this operation. So, since we have a stride of 2, we insert 1 or S minus 1, we insert one row of zeros and one column of zeros into the feature map of size 2 cross 2, right, and there was no zero padding here. So, which means that we act, so the everything is reversed. So, that to understand this, so since there was no zero padding here, we have to do a zero padding when we do the transpose convolution, if you think of it that way. So, we have a padding of 2, right. So, in order to get the appropriate size feature map, and your stride is 1 as before. So, and your stride is again 1. So, if you do the convolution as like a naive convolution or your usual convolution with this particular input size, then you will end up with your 5 cross 5 feature map. Okay. So, this transpose convolution is typically is the one that is often used in encoder decoder networks or in any situation where you have to upsample your feature maps. Another way of looking at it is that, let us say you have a network, right, and bunch of feature maps. This is a CNN, let us say, typically where you have a bunch of feature maps, okay. This is your forward pass, through the network, okay. So, you get your output, right. So, we know that to get from the input to output, it is basically a sequence of matrix multiplication. So, if the weights in every layer is this W2, W3, so on, just to be slack with the notation here. So, the output will be a sequence of matrix multiplication, right, W1x, and then you would have so on and so forth, right. In this case, if there are L layers, then you have WLX, right. So, this is your output. This is during forward pass. Now, during the backward pass or back prop, your gradients are propagated by transposed matrix multiplication. Right. So, the error you back propagate in this direction. So, as you notice, if you are back propagating the error from the smaller size feature map to a larger size feature map, which means here you are actually doing an operation which is same as the transposed convolution. Okay. That is the way of understanding transposed convolutions.